off by sharing my screen. So where are we? Okay, there. So you should now see my screen. Is that correct? Great, fantastic. So yeah, so obviously, Biljana, you were here for the early career researcher workshop earlier. This will be a very similar theme, but we'll extend it. If you see me squinting, I'm just trying to make the Zoom screen as big as I can see you. There we go. Struggling with my cursor. Right, there we go. Now I can see. Fantastic. Okay. So yeah, what we're going to do in this session is extend. There's some repetition, necessary repetition, because we'll talk about how to get data from the same archive, but we'll be going a bit further, considering what heat is and why temperature, perhaps, depending on our application, but temperature may be not enough for us. So we need concurrent observations of other variables. So without, before I give the whole talk, before changing any slides, I should kick on. I should actually start changing. So this session will be very similar to the early career one earlier in format, in the few opening slides. There will be a few opening slides covering some key ideas, and then the majority of the session will be a somewhat self-paced programming workshop using these using another notebook, Python notebook. So the opening slides will consider some key variables that we should be aware of when we're dealing with heat as properly defined, total heat content of the atmosphere. That's very relevant in the context of human heat stress. So thinking about heat from the perspective of human well-being, health, and also economic productivity. I'll say a few more words on that. In some cases, temperature is fine, but we'll be talking about key metrics in the context, particularly of human heat stress. And then where we repeat some of the early career research material is in talking about how we can access, well, firstly, what are some archives of weather stations that hold the necessary data for us to compute human heat stress, and how do we get access to them? How do we automate analysis for lots of weather stations worldwide? And how do we compute the relevant metrics from the raw quantities that are observed? So there's a bit more complexity, Biljana, compared to this morning, in the sense that this morning what we had was already there. The temperature data, we just had to read them in. That was the programming bit. Here, when we deal with as you'll see, humid heat, we often have to compute other quantities from those raw observations. So there's another layer of complexity. Okay, then, so let's actually talk about it properly rather than just introduce it. So dangerous heat, I know I'm preaching to the converted here, I suspect, but it never hurts to underline the importance of heat as a dangerous hazard worldwide. We're well aware of this part of the world, temperate mid-latitudes of Eurasia. We had the European heatwave 2003 that really caused a lot of people to sit up and take notice of extreme heat as a threat. Varying numbers of fatalities attributed to that event, but some go as high as over 70,000 fatalities. Majority in mainland Europe. France, I think, was the epicenter of that particular heat wave. The UK, interestingly enough, recorded its, I think, third highest temperature. It was the highest temperature at the time of 38.5 degrees in Kent. So it does get that warm over here occasionally. Since been broken twice, that record in 2019, and then a new second place was set in 2020. So big threat worldwide, extreme heat, and we're probably vastly undercounting the impact of extreme heat as a hazard. We see in the table on the right where extreme heat ranks compared to other hazards. And I've called out the European heatwave of 2003 and the Russian heatwave of 2010 as key examples of very high impact events. But it's worth pausing and just reflect on this for a second. One, it's not just extreme heat as the direct cause, rather extreme heat wasn't necessarily the direct cause of all of those fatalities. In the case of Russia in particular, had a high pressure situation, led to episodes of very poor air quality that were related to large-scale forest fires that went in unison with the extreme heat. Not necessarily the extreme heat's direct pathway to mortality. That's one thing to note. Secondly, we don't necessarily have access to necessary health monitoring data from other parts of the world that are much hotter and more humid and experience greater heat stress. Places like Pakistan, India, Bangladesh, the Gulf states, South and West Asia are the hottest and most humid places on Earth. And it's quite likely that we just don't know the full effects of some of the extreme heat episodes that have afflicted those regions. In 2015, there were heat waves in Pakistan and India separated by a few weeks that officially killed around 2,000 people in each event. But they are quite likely huge undercounts. So I just want to point that out at this point because the two problem examples are on our doorstep, and it's tempting to think that this is perhaps a mid-latitude problem. But the anecdotal or case study evidence from places that do have available data indicate that we do get transient periods of extreme humid heat in places that are already very hot and humid, and people die as a result. We probably don't have access to sufficient health surveillance data to really accurately capture the impact of extreme heat in those places. Of course, the other side of the coin is the sort of our urban structures, our environments, our culture, our way of doing things, operating extreme heat. Our learned behaviour is not as sensible in the mid-latitudes. We're just less good at coping with heat. Our physiology is quite similar, interestingly enough. In terms of if you grow up in South Asia or you grow up in mid-latitudes, our physiology is quite similar with respect to how we can deal with extreme heat. But our learned behaviour is very different. So and the structures that we live in are very different too in terms of how good they are at coping with extreme heat when we don't have things like air conditioners to depend on. So a bit more than I wanted to say on this slide, but simply to take a step back, and the big picture is extreme heat is a really big problem already. We know this, it's on our doorstep. It's probably an even bigger problem than it appears from alluded to on this slide. And it's inevitable as air temperatures go up. We can we can do lots of research figuring out how bad it will get, but simply as the global mean air temperature rises, the danger, the potential danger from extreme heat will climb accordingly unless we adapt very cleverly. So growing problem is the other thing to point out. It's worthy of our focus. A long-winded way of saying good that we're looking at extreme heat. So what do I mean by extreme heat? Well, temperature is one very important component of how hot it feels, but it's by far the only thing that's of relevance in terms of meteorological quantity that influences our thermal comfort. Our thermal comfort is influenced by heat exchange between our body and the surrounding environment. So the schematic here actually pulled from a very obscure paper on thermal comfort in automobiles, but it does the job for highlighting some of the key heat fluxes. So we're generating heat internally all the time from metabolic activity, and our core temperature around 37, 38 degrees to be maintained, we have to dissipate that heat to our environment. If we don't, it will build up, it means our temperature will climb, and ultimately it can't climb very far away from that point before we get into real trouble. So we need to dissipate that heat to our environment. How do we dissipate the heat? Well, there is some via respiration, sensible and latent heat transfer. Latent heat transfer is the change of state. So evaporating water releases latent heat. That's a cooling mechanism. Then from our skin, we have radiative transfer, long wave thermal radiation emitted by us at our skin temperature of 300 Kelvin, radiating out the surfaces around us, radiating back towards us. Often quite a bit cooler than us, so radiating less. So the environment is typically a long wave or thermal radiative sink. If we're outside and in direct sunlight, then solar radiation, sunlight instant upon us, is a major source of heat gain. And then we also lose heat to the atmosphere, or we can gain heat to the atmosphere via sensible and long wave and latent heat transfer. So the air scouring across our skin can exchange sensible heat with us, or allow sensible heat exchange between us and the atmosphere. And the act of evaporating sweat from our skin is a very important, I'll show you in a minute, very important way of cooling down. Evaporation consumes latent heat, cools our skin down. So in terms of meteorological variables that we all need to be aware of when we're thinking about human thermal comfort and human health, we need to know about the humidity of the atmosphere. The humidity of the atmosphere is critical because it determines the potential evaporation rate of sweat on our sweat from our skin. Also, to some extent, the amount of evaporation from our lungs as we respire, but most importantly from sweat on the skin. So we need to know the humidity. We also need to know the wind speed. The faster the wind scours across our skin, the more efficiently evaporation can proceed, and also the more efficient sensible heat exchanges. The quicker our skin will come into equilibrium with the air that's passing over the surface. So a few things to be aware of there. If the air is warmer than our skin, it heats us up quicker, the stronger the wind. If it's cooler than our skin, it cools us down quicker, the faster the wind. And our skin temperature, by the way, needs to be around 35 degrees Celsius. If it climbs above that, then there's not a sufficient gradient between the core and our skin to keep our core safe temperature. So we need a skin temperature no more than about 35 degrees. And one thing that's important to appreciate at this point is that if the air temperature goes above 35 degrees, then there's a source of sensible heat gain to us. And the faster the wind blows, the more it heats us up. We rely on sweating once it goes above 35 degrees as the primary mechanism to keep ourselves cool. It allows us to enter into environments and stay there that are above 35 degrees Celsius. But just stepping back, we need to know really about these variables too, these meteorological variables, if we want to quantify human thermal comfort. Okay, and what's most important there for our analysis, when we think about analysis, when we think about behavioural modification, etc., to cope with episodes of extreme heat, we can sort of rank those variables in importance. To recognise, have a complete to understand human thermal comfort, we'd actually need to run energy balance models with all those variables in to figure out how hot it feels for us. That's a difficult thing to do, though. Computationally, it's quite can be quite heavy and requires lots of variables too, as we've just outlined, and they're not recorded in many places worldwide. If we're talking about radiation, radiative fluxes recorded at a fraction of the tens of thousands of weather stations worldwide. I don't know the exact number, but we're probably talking about no more than 1,000 or so. Very well monitored places that traditionally are quite well monitored. So it turns out we can legitimately, without worrying about the availability of data, we can actually drop down those radiative parameters quite low in the priority table of things we want to know about to infer human thermal comfort. The reason for that is that we can, so one of the first things we can do is we can control our radiative environment quite well by, for example, retreating to shaded, sheltered locations. So when it's extremely hot, get out of the sun, so we can remove shortwave radiation entirely sunlight entirely from our thinking about human thermal comfort. And if we are out the sun, it's quite likely that the surfaces we encounter will be the same temperature as the air. So that can tell us something, allows us to estimate pretty well the long wave radiative exchange as well. And if we're outside, somewhere sheltered, we actually don't have many surfaces around us to exchange long wave radiation with. And we're probably going to be, if we're sheltering, we may also be out of the wind. So we can say the radiative fluxes and the wind, we may be able to drop in our assessments of extreme heat, because they can sort of approximate where they may fall and that they may be limited in their importance. But it's very difficult to get away from the enthalpy, the humid heat content of the air. So it's the temperature and humidity of the air. We can change the relative humidity by simply pumping up the temperature, but it's hard to get away from those water molecules. Okay, so the air temperature and the specific humidity are hard to escape from. So that quantity I'm talking about is the enthalpy of the atmosphere, the moist enthalpy, which is the sum of the sensible and latent heats. And the sensible heat is just the air temperature multiplied by the specific heat capacity of the air in joules per kilogram. And then the latent heat content is just the mass of moisture in the air multiplied by another constant, the latent heat constant. So we're looking there at the sensible and latent heat content, sensible and latent heats per unit of atmosphere, so per kilogram of atmosphere. And the sensible heat content is proportional to the temperature, the latent heat content is proportional to the mass of moisture. And we feel that, we feel the enthalpy. We don't just feel the air temperature, we do feel the amount of moisture in the atmosphere too. Why? Because it limits the efficiency of sweating. And as I alluded to previously, I said if we go above 35 degrees in the air temperature, then the air is a net source of sensible heat for us. And we can only dissipate heat. We remove, forget the rates of exchange completely for now. It's the only mechanism with sensible heat transfer. Once the air temperature goes above 35 degrees, we've got no way to dissipate our metabolic heat, and we're going to cook and expire soon enough. We can't dissipate that heat. So anywhere that goes above 35 degrees routinely on Earth would be a place that humans can't live, essentially. And around 80% of the world's population live in areas where the annual maximum temperature regularly goes above 35 degrees. So another way of framing that is about 80% of the world's population regularly rely upon sweating to survive. It's a very crude but useful ballpark statement to convey the importance of sweating. So the point I'm getting to is, we talk about human thermal comfort. It's more than temperature. It's quite a lot more than temperature. The simplest perspective we can take on this is also quite useful, is to include humidity, the moist enthalpy of the atmosphere. So the temperature and the humidity of the atmosphere. Those things together are critical in looking at humid heat. Or rather, humid heat is critical in looking at human thermal comfort, which in turn is important for human health and economic productivity, as we'll see shortly. So there's a huge number of measures of humid heat that are empirical metrics designed to try and capture how hot it feels. Things like the heat index you'll have heard of, the Humidex, the simplified wet bulb globe temperature, the universal thermal climate index, the perceived temperature, the median predicted vote, or whatever that measure is called. There are literally tens, if not hundreds, of humid heat measures that have been empirically derived to try and relate the temperature and humidity of the atmosphere to how comfortable or uncomfortable it feels. But amongst all of those quantities, there are two that are perhaps the most, but particularly useful. One may be familiar to you already, I think, the wet bulb temperature. The second is the wet bulb globe temperature. The wet bulb temperature, you'll see, is, I haven't given an exact equation for this because it's quite complicated to derive or to compute. So just now I've just expressed it as a function of temperature, humidity, and pressure. So T is temperature, Q in particular is the specific humidity, and the air pressure. So we compute the wet bulb temperature from those quantities. There are empirical shortcuts, so exact analytical but shortcuts to compute the wet bulb temperature. We'll use one of those in the workshop. To compute it properly involves actually using an isobaric chart. The easiest way is to climb up to the lifting condensation level using the dry adiabatic lapse rate, then go down a moist adiabat until you go down to the surface pressure, and you compute the wet bulb temperature that way. It's called Norman's rule. But there are some shortcuts that we'll use in the workshop that are much quicker to compute the wet bulb temperature. I'll come on to why that's so important as a metric on the next slide. The other commonly employed metric is actually an extension of the wet bulb temperature, which is the wet bulb globe temperature, index to estimate the total heat load on humans. And in its full version, it includes a term for accounts for solar radiative heating as well. So it can be used to a really good index to capture how hot it feels in the sun, which is important for, you'll see this metric has a history in guiding safe operation or safe activities in military and industrial settings. The military often need to operate outside, so they need to know the increased heat load of, they exclusively need to operate outside, you could say, so they need to know the heat load from solar radiation too. In the form that you normally see in the research literature, again, this simplifying assumption that humans are in the shade is applied. And then we can use a simpler version to compute the simpler equation to compute the wet bulb globe temperature, where we neglect the solar radiative heating, and the wet bulb globe temperature is then just a weighted sum of the wet bulb temperature, TW, and the dry bulb, which is the normal air temperature. So a weighted sum of those two components. So why are they why are they so useful? Well, the wet bulb temperature is well named. It's a temperature a thermometer would have if the end, the bulb, was immersed, wrapped in an infinitely wet wick. It's a bit of cloth that's wet, and it was swung around in the atmosphere. So the air can pass over that bulb, the wet bulb. Evaporation can take place, and that lowers the temperature of the bulb. So it's lower than the dry bulb air temperature, the normal air temperature that you're used to hearing about. Why is that an interesting and useful metric? Well, because that's how we keep cool, isn't it? Sweating. So the temperature of the wet bulb is a good index of how warm it feels for us once you factor in our ability to sweat and dissipate heat that way. The evaporation of the water on the bulb is equivalent to the evaporation of sweat from our bodies. So it's really useful for understanding how hot forming the basis of how hot it feels once you factor in the evaporation of water from the surface. So it's really useful for that. And it's been used, it's got a lot of attention since about 2010 in the climate change and climate extremes community, because it was pointed out that it identifies the absolute upper limit of human thermal tolerance. Because if we need a skin temperature of 35 degrees, then we can say once the wet bulb temperature goes above 35 degrees, that's it. We can't exist in that environment unless we're dumping ice cold water down our our throats every few minutes to lower our core temperature another way. And that way it's ingesting a cool substance to keep our core temperature low. Otherwise, if the wet bulb temperature goes above 35 degrees, it means even when we factor in the ability, the role of sweating to keep us cool, can't bring our skin temperature down but below 35 degrees, or can't keep our skin temperature at 35 degrees. Our skin temperature would rise, that means our core temperature would rise. We've got no tricks left once the wet bulb temperature goes above 35 degrees. Remember that we're already assuming there is no radiative load on us. So it's the absolute upper limit for the conditions that we can endure. Could you endure them for a few minutes? Yeah, of course you could. You've been in a sauna, you've experienced wet bulb temperatures above 35 degrees. But have they been experienced anywhere on Earth? Only in a few spots and only for a very, very limited period of time since humans have been on the surface of the planet, ranging widely. So this research in 2020 showed these are the counts of wet bulb temperatures above 35 degrees through time, and that size that you see there is one occurrence worldwide out of 10,000 points. They're exceptionally rare, but they're starting to emerge more consistently. Where are they emerging? Around the Persian Gulf. Persian Gulf is when we factor in, we treat heat holistically, and we include humidity, so talking about the moist enthalpy, hands down, the hottest, most humid place on Earth is the Persian Gulf, and specifically it's over the waters of the Persian Gulf. Bizarrely enough, it's the sea breeze that will kill you in the Persian Gulf in several decades' time. You don't want the water coming, you don't want the air blowing off the Gulf. So the wet bulb temperature is one, it's a useful general index of how hot it feels, the human body, and it's received a lot of attention because of its potential to capture this upper limit of human thermal tolerance. There's been a lot of research that's shown if we warm consistent with an RCP 0.5 scenario, there could be large parts of the Earth's surface that cross that threshold. Which I don't know how if you've heard of this before, but I think it's one of the really shocking projections of climate change. We're talking parts of the North China Plain, home to about 500 million people, that will regularly experience temperatures wet bulb temperatures above 35 degrees. Remember, this is where millions of people are involved in agricultural production, have to be outside during large parts of the day. Elsewhere in the Indus Valley in Pakistan, parts of India, I think, certainly parts of the Persian Gulf would cross this 35 degree threshold as well. So just to be clear, unless you have another method of cooling, which is invariably air conditioning or access to cold water, that must be chilled for energy production or energy use, you don't have a way of coping with the heat. So that's why the wet bulb temperature has really been very popular in this section of the extreme heat research. The wet bulb globe temperature is very widely used because it has a long history of being used to guide safe working practices in industry and in military activities. So there's a lot of research that's been done identifying safe levels of the wet bulb globe temperature for activities at certain intensities. Intensities measured in terms of calories, so actual work output, so calories per hour, per minute. So there's a long history there, and what that's used for is identifying how much labour, so productivity, may decline as the climate warms. So in order to keep to safe working practices, how much will we have to rest per hour in order to be safe according to the wet bulb globe temperature limits? How much will warming impinge on our ability to perform work, using the true expression of the term work, so using energy. So it's got a long history of being used there, and it's been used most famously, I suppose, in the recent research literature in 2013 by Dunn et al. Paper in Nature Climate Change, and looked at the reduction in global labour capacity as a function of climate warming in these different RCP projections. So you can see, according to, I think these are the monthly maximum values average worldwide, you can see that by 2200, we're looking at maybe the hottest months, work is 50% of the full potential. So losing half the amount of the work you can do. Of course, this has huge implications for humanity's ability to feed itself as well as do everything else, assuming that mechanised production doesn't take over. So that was a bit of a segue, but those two metrics are key. Wet bulb temperature, upper limit for humans, wet bulb globe temperature, extension of the wet bulb temperature has a long history in defining safe limits for different levels of intensity of activity. So both widely used in the research literature on extreme humid heat. Okay, so if we want to start analysing extreme humid heat, how do we do it? And Biljana, you'll recognise this as familiar from the session this morning. But I'm arguing that local conditions matter for this kind of analysis. An example of that on the next slide, but local conditions really matter, because we can see from what I just said previously around these hard limits, 35 degrees is set by our physiology. And those wet bulb globe temperature limits are also set by our physiology, and they've just been worked out by a long history of studies that looked at people's ability to work safely and the corresponding wet bulb globe temperature. So absolute values matter at the point that those activities are being performed at, or the places that people are living. Absolute values matter. From gridded products like reanalyses data, we get what's going on in the general region. We can track variability. A reanalyses data set may be perfectly correlated with, let's just give a concrete example. We can have reanalyses data from a grid cell over Karachi that may have a correlation coefficient of 1 with the weather station that's in Karachi, but may have an offset, may have a cool bias in the wet bulb temperature of 1 degree. That difference really matters if you don't know it's there and you are looking at the frequency of dangerous events through time. It matters which side of 35 degrees you're on. You know, over 35 degrees, not sustainable, below, sustainable. So the local conditions really matter. We only get those with weather stations. Reanalyses data can, if we know that, we do a comparison and correction, yes. But if we're looking to the gold standard to work out how extreme the conditions are that people are experiencing, there is no substitute for real weather stations on the ground, real observations. And in the context of humid heat, we need a bit more than just air temperature, as alluded to, which makes our requirements a little more difficult than we talked about this earlier on with the early career researchers workshop. The training missing bracket here. But we need concurrent observations of air temperature, humidity, and ideally surface pressure if we're going to evaluate the wet bulb temperature too. And some other quantities we might want to derive require the air pressure. So we need 3 quantities rather than 1. So we're going to be limited compared to air temperature or precipitation as another variable that's often looked for or needed in coverage of extreme events. We're more limited because we need concurrent observations of multiple variables at the same point in time and the same point in space. So a really good archive that has access, that provides access to said observations is the integrated surface database. Hourly resolution, storing ideally or often those variables for each station, actually a lot more. Not every station has all those variables. Some stations have many more. This is the archive that one of the archives that does provide routinely access to the key metrics, key variables that we need. And as earlier, there's a very useful data set that is a subset of this integrated surface database that holds quality controlled subset. And that is the HAD ISD produced by the Met Office Hadley Centre. So quality controlled subset of the integrated surface database, ideal for analysing extreme humid heat weather stations. So you can follow these slides that are in the shared folder. You can just click on the blue text as a hyperlink through to the homepage, landing page for that data set, so you can read about them there. Okay, I'll skip over this. This is just showing you the difference between reanalyses and so I'll skip over, I'll talk about it very briefly. This is showing the difference between reanalyses and weather stations and why you need weather stations to analyse extreme humid heat. Reanalyses, these so subtropics top row, tropics bottom row. Orange is reanalyses, extremes, and across all the grid cells in the regions indicated. That's longitude bands in the columns, and say latitude bands in the rows. The issue to point out is the reanalyses systematically underestimate the extremes. So just making that point, illustrating that point that we need the observations from weather stations. And I said that where do we get them from? We get them from the HAD ISD, is probably the most convenient, user-friendly point to get those data. So they've been quality controlled already, and they contain the weather stations, and they largely contain the variables that we need. So how do we get access to them, particularly if we want to do all those things that attract us to reanalyses data in the first place? Things that attract us to reanalyses data, if you're into programming and sort of big data analysis, the thing that attracts us is the ease with which one of the things is the ease with which you can look at big emerging features. You can do analysis for lots of locations worldwide and get an impression of overall change, places that are changing most rapidly and where issues are perhaps, or in this case to be specific, extreme heat and changes to it are perhaps of most concern. Reanalysis is great because we can easily scale our code to run worldwide, any location, very nice. How do we do the same when we're talking about accessing weather station data? There's often a bit of a jump from accessing individual weather stations, which is quite easy with different tools to click on, fill out forms and download data from one or two weather stations. That's fine, but if we want to do the big stuff, we need to use some programming tools to help us. And I won't say too much on this slide, like I said it in the early career one earlier, and I just can't stand repeating myself. But interpreted programming languages can make life really easy for us. Python and R are two examples, but there's many others. Julia, MATLAB, Java also have similar functionality to allow us to grab data off the internet and process it. And if we can do that, we can grab and process for a weather station, and we know the rules, the structure of accessing. There's nothing stopping us from doing it to every weather station worldwide. That's the exciting bit for sort of big data analysis. And we're going to do that in the programming workshop bit for the rest of the session. We're going to practice accessing the HAD ISD using Python and Jupyter notebooks. And the one other thing I'll say is that the method we're using is kind of the last resort. It's when the archive that you're trying to access isn't set up for programmatic access. Some archives are. You'll go to the web page, for example, the global summary of the day, and you'll be given instructions for how to FTP to the server, and then how to programmatically take data down. Or some other archives will have a specific custom API for you to interface with those data sets and pull them down. There'll be guidance on the respective web pages for how you do that. In cases where that hasn't been set up, where there isn't an FTP server, there are still ways in which you can programmatically grab data. All you need is the URL of the data and the assurance or the condition that those data are not behind some sort of security or firewall And the method for doing this last resort of data scraping, in Python, an easy solution is the requests module. As long as we know the URL and the data aren't protected, we can grab them, and then we have the file, and then it's all ours. We then use all of our tools that we pick up through time, and I'll show you the tools in the Jupyter Notebook. But in terms of how you generally do this, you first get used to dealing with local files on your computer, how you programmatically read them into a format that is suitable for the type of analysis you want to perform. If it's time series data, it's read into a structure or an object in Python that is set up to deal with time series data. In this case, we use the pandas data frame. So get used to doing that with a local file first. And then the extra bridge here that I'm providing is to show you how to grab data from an arbitrary URL, bring it in, process it. In this case, we have to turn it from a zip file, we have to unzip it, then it's a netcdf file, we have to read the netcdf file into a format that's really easy to use. The workshop bit that we're about to kick into, it's basically a how-to. It shows you how to do all this with some text description, the appropriate code you can run and produce the outputs you need, and it acts as a template for anything for you to do in the future. And Brianna, the exciting bit here is the solution to downloading all of the weather stations worldwide is actually in this notebook. So you can run that and you have it. So it's a template if you want to do any analysis with the HAD ISD, so any humid heat analysis, you want to use weather stations to assess, for example, the 2007, 2015 heat waves in Serbia and Balkans. You have now the code to do it. This can be used for that. Okay, so I'll just show you the notebook. So just to share my other screen. So bear with me while I sort that out. Log into my Unix machine. Okay. So if you didn't know, you can see this. This is I can't make it any bigger, but this is a Jupyter notebook that I've shared with you. So hopefully you had the instructions that show you how to launch a Jupyter notebook. The instructions I gave you will get you to this screen. If you've got Anaconda installed on a Windows system, then you can get to this point by either launching the Jupyter notebook from the start menu. You go to start, Anaconda, 64, 32-bit, drop down menu there. One of the options will be Jupyter notebook. Click on that and it will launch in your home directory. And then if the file that I shared, the IPython notebook, which for you guys is srs.ipynb, if that's down down from where you land in your home directory, so there's a subfolder of that, you'll be able to navigate to it within this window and launch it by clicking on it. Or you can also launch it from Windows by opening the Anaconda prompt, CDing, changing directories, type CD and the path of the directory that this notebook is in, get into that folder and then type Jupyter notebook and it will launch and open a new browser window in your browser, and then you'll get to this point and you can click on the notebook by launching it. So you'll be there and you click on the notebook by clicking it, and up it pops. And the thing that's special about Jupyter notebooks is you'll see it looks like a normal PDF. So we have text here that's a story for you to read, and part of that story is code. So this is Python 3 code, and you can run this code in your browser and it will produce output required, will produce all the required output. So the idea is to treat this like a story with key bits of the story. The story is the text, the key bits of the code. Read it, run the code by either can press Control and Enter. That will run it, or you can click Cell and then run cell or run all. I recommend you don't run all because it will ruin the story. Just do one at a time. Just click in there and click run. There are many ways to do it. I recommend, I'm lazy, click in there and do Control Enter, and it will run that particular a particular cell. You can see it's been run. I'll just clear all output so you can see what happens. When I go in here, you'll notice very quickly it's turned to a star, then it will have the number 1 in there that tells you it's been 177. I think it's still registering this as an earlier session. Maybe because I've got it open there. It's still giving me 178. But anyway, the transition from no number to a number in there tells me that the cell has run. The reason why I'm explaining this, there are some cells you'll run and you won't know anything's happened, but then it's still necessary to run. This first cell is important because, so I don't know if you're familiar with Python, then I apologize for stating the obvious. If you're not, then this will be important. But this first cell is importing modules, which are basically toolkits into Python that allow us to perform more complicated or more involved analysis in a very straightforward way. For example, how do you calculate the average of a set of numbers? We know how to do that, the arithmetic average. Does Python know how to do that? No. As it is, you would have to spell out how to compute the average, add up all the numbers and divide by how many numbers you have. That function, the mean, the arithmetic mean, is defined in many Python modules. For example, in NumPy, numerical Python, to calculate the mean, we would just type in numpy.mean and give it their numbers and compute the mean. So there are lots of functions and other useful things that are hidden in these modules that we can use. To use them, we have to import them like this. Now, it is worth me pointing out a few other things in this cell. The definitions that you see are me defining some functions that will be useful for us in the context of the workshop. And a function is something that does something. In this case, those somethings are taking quantities observed at the weather stations and returning other useful quantities that we need in the context of our analysis of humid heat. The first, so I'll talk you through a couple of them, or maybe all of them, but only briefly. I'll just tell you what they are. More detail for the first, less for the rest, and then got to get on and do some workshopping soon. So the first one, def sat vp. This is define the function saturation vapor pressure. So we're computing the saturation vapor pressure. That's the amount of moisture that the air can hold for a given temperature, and using this expression from Juan 2018, a simple empirical approximation, and the reference is provided in the description. And so is well, in the description it's also telling you what the inputs and outputs are for the function. The input is temperature in Celsius, the output is saturation vapor pressure in pascals. And a warning that no error checking is performed. So the function is not going to check for Celsius versus Fahrenheit versus Kelvin. So you have to make sure that you put Celsius in. And then there's the function written there. So normal mathematical equation, but with some programming quirks that include sort of logical indexing and some other things. But otherwise, don't worry about the Python, particular Python code for now. Just appreciate this is a function that's really important in the context of humid heat because it's computing saturation vapor pressure from temperature, which turns out to be something that we need later on to compute these other derived humid heat metrics. One is the relative humidity. So we go from the dew point to the relative humidity. That's another function that's in here. I apologize, the story I'm telling isn't in quite the right order here for the order in which we want the humid heat metrics to be derived. I'm just talking to the order in which they're presented here. But in the HAD ISD, we have dew point as the variable that's recorded. That's common because dew point is the variable that's measured at many of the weather stations worldwide, or at least that's the way the humidity data is shared. It's the dew point, not the specific humidity, not the relative humidity, it's the dew point. So if you want relative humidity, we need to convert from dew point to relative humidity. So here's a function temperature. That's a way of getting us the relative humidity. And then here's a way of calculating the wet bulb temperature. The easiest is an empirical approximation. That's very good for sea level pressures, but not very good once you get away from sea level pressures. For our purposes, what does that mean in terms of the study of humid heat? Well, it means in the hottest, most humid places worldwide, it's a good guess because the hottest, most humid places worldwide are very close to sea level. So this is an empirical function to compute the wet bulb temperature from the temperature and the relative humidity. Compute the relative humidity of the function earlier. This empirical approximation comes from Stahl 2011, widely used empirical method, and the function is down here. So this computes the wet bulb temperature from T and RH. And then finally, I've given you the function for the wet bulb globe temperature. Remember, that's easy once you have the wet bulb temperature and the air temperature. It's just a weighted sum of the two. And for convenience, I've defined the function in a way that will take just the temperature and the relative humidity and compute the wet bulb temperature inside, and then return the wet bulb globe temperature. Another function there is to compute the distance between points. And this is useful because, as you'll see as you go work through the handout or the notebook, we want to get data from weather stations that are close to whichever point we're interested in. And to do that, we need a way of calculating the distance across the surface of the Earth, to the curved ellipsoid, given different coordinates. So this is a function that will do that. We'll take latitude, longitude pairs and compute the distance between them. And that gives us a way of finding the closest point to anywhere that we're interested in. So they're all the functions. And then, so to run, the reason why I explained that in the first place was because when you run that bit of code, and I'm pressing Control and Enter at this point, so I'm running that bit of code, it went briefly, it's gone blue, it turns green again when I click somewhere else. You don't see anything happen. Okay, that's because we haven't asked it to output anything. It's just registering all those functions, doing the imports, registering the functions. Once we've done that, we're then ready to work through the rest of the notebook. The only thing you need to be aware of to change the first time you run it is this, the directory that you've got the had ISD metadata files saved in. That metadata file is simply the lat longs and elevations of all the weather stations in the had ISD archive. For full transparency, I got that, provided it to you by going to the Met Office Hadley Centre website for that data set. It's not this page, but it's one. It's there, I think, that one. That link, you can see my mouse, that'll get you the CSV file that I've then shared with you. You could have done this yourself. I just thought it'd be easier to remove that barrier for you. But if you're doing something like this again, you know, this is the way that you can source that metadata information. It's always there somewhere if you look on the website. It should be. So you need to be aware of changing that the first time through. The other thing to be aware of, I think, I'm not sure if that is now, that's the right, oh, so Belgrade this time. I've put the lat longitude in for Belgrade, so the code will do the first time. If you don't change these numbers, the code will pull out, identify the closest weather station to Belgrade, and then it will download it and read it in for analysis. So I'm keen to not just talk at you for any longer. So have a go at running the notebook. Let's say 40 minutes or so. You'll see that to run it all doesn't take any time at all. You could just run all the outputs, everything's done, and that's instant. But what would be helpful, I think, for you to do is to read through it all. If you're not familiar with Python code, just reading the comments to understand what the bits are doing should be enough. And that's all you can really do at this stage, and read the text in between too that helps explain what's happened. If you do know Python, then read it in detail so that you can see what each line is doing and appreciate what type of functions are out there from pandas, one of the modules that's really useful for time series analysis, from the NetCDF library that allows us to read in NetCDF data. Basically, if you know more Python code, look at the details, you can see which functions are available for doing this type of work. And what we'll do at the end is, so in 40 minutes time, is I'll talk you through all the blocks of code again to highlight the main things they're doing. And then we'll go through the actual kind of climate change impacts case study that we do here. Very simple, just working out how much of the hottest hour on average would be lost because we'd have to rest. How much of that is currently lost under the current climate, how much would be lost for a simple climate warming scenario. We'll run through how we can do that with these simple tools and the types of human heat metrics we're doing, and then I'll talk you through some of the going further bits at the bottom. So we'll come back in 40 minutes to discuss effectively those bits, but ask questions in between. So I'll be here throughout. I'll just put myself on mute until get a question. But I'll be past the hour that we'll run through everything as a group again. Does that sound okay?
Yes, so we will be back at 5:30.
Yeah, I mean, I'll be here throughout, so of course just ask
Okay.
questions, but I'll start talking again actively and let's ask them before.
Is it okay if we ask questions just to turn off our microphones and
Yeah, of course. Yeah.
Okay.
Of
Okay,
course.
thank you.
You're welcome. I'll just put myself on mute for now so I don't make a racket drinking my drink here. Everything's fine. Sometimes the compatibility issues, but mostly it's a really easy way to fix things. Okay, so I'll just share my screen and we can talk through the key bits. And that one. Just drag Zoom across. Okay, so hopefully you can see the notebook. Yeah, and is it the right size? Is it? Yeah, I can see it too actually on the image. Yeah. Okay, so yeah, lots of this is just following the story, running things. We spoke through the function definitions earlier. Then this has been familiar to anyone that was in the earlier session, where I discussed how to actually grab the data. So we were changing the directory, and that can be a bit tricky if you're not used to defining file paths in Python. And one gotcha is that indeed the slashes are the other way around in Windows, if I recall correctly. So that can be tricky, but once you've done it once, you know about it, and all is good thereafter. Now, the heavy lifting in terms of actually accessing the data sets, the online data sets, is performed in this cell. Once we've set those parameters and we've read in the stations file using this method available to the pandas library of reading in the CSV, we compute the distances between our query point and all of those other points, and then we can identify the closest station to where we want to assess. And I've been curious, and I've already changed this to Doha because I know Belgrade quite well by this stage. I've been on this script several times. The lat long I've got in here correspond to Doha, around the Persian Gulf, one of the hottest and most humid places in the world. So the output you'll see here will be Doha. So then the getting bit, the magic is down here. And so apologies for repetition from earlier, the work of earlier, but this is the sort of the clever bit, the detective work bit, the URL base. So you can get this, figure out what this is, what the URL is. The base, I'll explain what the base is in just a moment, but you get this by going onto the HAD ISD page, clicking on any of the weather station files, clicking copy link address and pasting it into a notepad, anything, to inspect what the link address actually is, the URL. Do that for a couple and you see that they share the same beginning, as is to be expected, and just that there's an individual identifier for each station at the end, which is the ID that we've already read in when we had a look at the station file. You can see that the first column is the weather station ID, this 11-digit code that's outlined in the notebook. And that forms the rest of the URL. Just need to scroll across. I've lost the ability to scroll across. How do I do that? I think I have to restore. Sorry, so you can see I've already got the right-hand side of the code cell here. I can't see how I minimize. That's a pain. Oh, sorry, there it is. Got it. Magically, I can do it again. Okay, so we build the full URL by taking that common base we identify from copy, link address, paste in, identify that the full URL has the ID included, and then we add the file extension at the end. And the ID is enclosed in this variable called closest that we defined up here. Closest has become the ID of the closest weather station, the one that is closest to those query points, using the distance function to compute the distances. So our final URL is that common base. It's the same for all the weather stations, the 9,000 weather stations in the archive, plus the ID, weather station ID, closest, plus the extension, which is a zipped version of a netcdf file. So that URL file is now the complete URL to grab that file. And then we use the magic of the requests module to actually do the getting. And the stuff that follows is a little more involved than it would be if we didn't have a zip file that we've retrieved. The code here takes care of downloading the zip file to a local file, unzipping it, and writing it to just a raw netcdf file, so unzipped. And then what we do next is we use netcdf library, netcdf4 library, which is a Python module designed to deal with netcdf data, which is the format that meteorological data, climate model data, etc., are shared in. It's really useful because it's self-describing, so all the units, etc., are included. Details for how the data are organised, the dimensions, latitude, longitude, time, pressure, being altitude in the atmosphere, for example. That's all communicated in netcdf files. So that's how they're commonly shared, or metadata are commonly shared. And there's a module in Python, netcdf4 module, that's built to deal with those data types. So we use that to open the file here using this dataset function. And then what follows is the required fiddling with the different bits in that CDF dataset to allow us to put those data into something called Pandas data frame. And Pandas is a fantastically powerful module for time series analysis in Python. So if you're new to this, and it's first time we've heard of Python, first we've heard of Pandas, but you've been heard of Python and tried some data processing, then have a good look at Pandas and see what it can do. We just use a few of the thousands of or hundreds of functions that it has in the rest of this code. What else do we do in here? Well, we limit the data to the 1991 to 2020 period. That's the recent climate normal, 30 years. Relatively good data availability for Belgrade too, just one missing year. So that's the other thing that goes on there. And you see the output here from that code cell. Mine's different to yours because I've just run this for Doha, being the latest. And we had to settle for a station that was around 100 kilometers from Doha. It says it's downloaded the file, also says where it's been stored. So that's, if you're new to programming, it's useful to do these sorts of things, to have output along the way so that you can, one, track any errors, and two, make life easy for yourself by pointing to exactly where you save the file. It can be quite a game when you've created a path from several variables. It can be actually quite an ordeal just finding out where you put the thing once it's downloaded. So I like to print things as often as practical. And then what do we do down here? Well, we use those functions that we defined earlier. Now you hopefully see that the power of them for allowing us to track what's going on. We defined them earlier, so we don't need to pollute our code here with lots of lines of calculating things. We now can compute the relative humidity and put that into this. The variable called recent is a data frame, a table of data in the created or in a format that the Pandas module understands. And we create a new column of data in that table called RH for relative humidity. And what do we put in there? We put the output of that due to RH function that we defined earlier. So you can see how powerful having a function is. We just call it, and we have the relative humidity placed into our data frame. If we didn't do that, we'd have to write the code out in this cell here to calculate the relative humidity from dew point temperature. Similarly, now we can just call that function to put the wet bulb temperature into the data frame, and similarly with the wet bulb globe temperature. And a sensible thing to do too, again, you're probably telling you things you definitely already know, but just in case you're not used to doing this sort of stuff, plotting where possible, if you're dealing with a limited number of stations where you can visually inspect data sets, always sensible to do it so you can spot any issues. So we make a quick plot here of the wet bulb temperature on the left and the wet bulb globe temperature on the right. See a nice reassuring annual cycle. We see quite a lot of missing data in here that we have to be aware of if we're doing anything sensitive to missing data. Almost everything is. So that's good that we spotted that at this point. It's also interesting to look at the values that we're getting. You would have been seeing for Belgrade, wet bulb temperatures between about -15 and 25 degrees Celsius, and wet bulb globe temperature between about, say, -15 again and 28 Celsius. Doha, or this area, station around 100 kilometers from Doha, is hot. We see values very close to 35 degrees. It's one of the hottest, most humid places in the world. And wet bulb globe temperatures also obviously a little higher still, because it's a weighted average of the two quantities, the dry and wet bulb. The dry bulb will be higher unless the air is saturated. Okay, so that's kind of that was a whistle stop of how you can grab data from any station, and showing you the use of these other functions to conveniently calculate derived quantities that we need to have if we want to inspect humid heat. And then an application of how we might apply those with a research question in mind. That research question could be, okay, given we have these well-established relationships between the wet bulb globe temperature and safe levels of physical work activity per hour, how much is work activity restricted by temperature if adhering to those standards in the current climate, and how might that change as the climate warms? So just using a really simple toy example of using the average maximum wet bulb globe temperature per month to compute the labour capacity. In other words, the average minimum labour capacity per month. And we're defining labour capacity following the Donatel paper, linked in the notebooks you're going to take you through to the study, using their equation to go from the wet bulb globe temperature to labour capacity. It's a percentage. 100% means you can do everything. The temperature, wet bulb temperature is not impinging upon your ability to do anything. It's always cool enough in the hour, you don't have to rest at all. Any value below that indicates you're having to reduce your work because of the wet bulb globe temperature being too high. So we compute that from our wet bulb globe temperature using this code below. There are other ways to compute it. This is quite a convenient way. We know that anywhere the wet bulb globe temperature doesn't go above 25 degrees, respecting this equation, we're going to have a value of 100% in there. So stick that number in there, 100% anywhere less than equal to 25, and then perform this calculation. So use the equations output anywhere the wet bulb globe temperature goes above 25 degrees. And then we use these really powerful these powerful functions of the pandas data frame. And I just highlight, I'm not sure if we've done any up to this point, but I highlight this really useful function here, showing you how we do something quite complicated in terms of sort of organizing rows of data. You think now it's just been reduced to a single line of code, which is a few words of code. We are resampling. So going from, in this case, if it's 3 hourly data, which I think it is for this station, it was for Belgrade, we go from 8 observations per day to 1 observation per day. So we're taking resampling, and the D stands for day. So it means go from whatever the frequency is to day. Just think about how convenient that statement is. Very easy to say in English or Serbian if you're saying it yourself in Serbian, but very easy to say. In terms of coding that, if the language you're using isn't time aware, think how fiddly that can get. We have to find all observations that are for the same day, and then find the minimum of those, accepting the fact that we can have lots of missing rows of data, we can have irregular sampling intervals. That it gets very messy very quickly. If you've ever had to code this manually, you'll be aware of the pitfalls that can be in there. The pandas library, the way in which we've read the data in, you'll see the code we've used earlier has done this. The way we've read the data in fact we've used pandas, means that the data frame or Python is aware of the time sensitive or time series nature of the data. So when we say resample the daily, it takes care of all the complexity for us. Really, really convenient. So we're saying resample the daily, we could put monthly, yearly, 3 hourly, 6 hourly, anything we want in here, resample, and then what do we do to those data? How do we go from those 8 values, it's 3 hourly data, to 1 value per day? Well, we're calling the minimum function. So take the minimum across those 8 values as we're asking for there. And then, as you'll see, explaining the code, we wanted to compute the monthly climatology of those minimum values for the labour capacity. And we can do that by applying this line of code here. Difference compared to the above is we're using the group by function. It's available to pandas objects. Group by is finding all the unique values of whatever we put inside the brackets and using those unique values to aggregate by. In this case, we're interested in the unique values of month. So all the 1s get averaged, all the 2s get averaged together. And again, we could take the max across them, the min across them, whatever. We decide that at this point here where we apply a function to the aggregated data. And then below is just a plot. And if you're not used to Python, this is we've done this earlier, so I won't explain it, but this is the generic way of creating a plot using the matplotlib module. And what we see, this is for Doha, very different to what you saw for Belgrade, where you just saw in peak hours less than 10% of the time, so less than 6 minutes on average would be you'd be required to rest for on the hottest day of the month, or hottest hour of the month. For Doha, during the hottest period of the year, you can't work at all in the hottest hours. And actually, even from May onwards, from May until October, you're severely limited in the hottest hours in terms of the amount of work you can do. The very hottest hours, you can't do any work at all. This isn't far from where the World Cup is being held, by the way, and where we're having, the building all those stadia. And there's a great Guardian article on the perhaps a huge number of heat-related fatalities that have occurred in this part of the world. No surprise when you look at climatology. So then below we have this climate change example where say, okay, now let's imagine let's just have a toy example of increasing the temperature and seeing how that propagates through to this impact metric, which is the labour capacity. We have all the building blocks here, and now I'll show you really actually quite realistic approach to doing this. The simple thing we can do if we're interested in humid heat, and this is done quite often, it seems to be quite a robust and reliable thing to do, is to increase the temperature according to a climate change projection. And the reason why that's quite a convenient thing to do is we're drowning in projections of air temperature change over land, over the ocean. It's available from almost all climate models at all resolutions, temporal resolutions, a very widely available field. And we can use techniques like pattern scaling, if that's familiar to you, to draw very large samples of plausible changes to temperature. And now it turns out that globally, at least, the global average relative humidity stays about the same as the climate warms. It seems to be what the climate models suggest. In reality, there's a slight decrease over land and a slight increase over the ocean, but on average, not much change when you combine the two. And regionally, there'll be more. It's more complex. But to first order, a useful approximation when trying to work out changes to humid heat as the climate warms is to increase the air temperature according to climate model projection, assume the relative humidity stays fixed, and then you can see what that does to these derived humid heat quantities like the wet bulb temperature, wet bulb globe temperature, and the labour capacity in this point, so propagating it all through. So our climate change projection is as simple as, in this case, adding 1 onto all the temperature values. It's not terribly realistic, but it's not totally physically implausible or ridiculous to do either. It's the simplest, possibly acceptable way of doing this. Of course, the +1 bit, well, that would in reality vary depending on how much climate change is expected, or how much global warming is expected to be amplified in a particular land area you're looking at. I mean, almost universally, it's an amplification of the global mean when we're looking at land temperature responses. For Serbia, I would estimate probably something like 1.2 to 1.5 degrees of warming per degree of global warming is what you can expect. You probably know better than me over that, but generally over land, we'll see more than 1 degree of local warming per 1 degree of global warming. Anyway, whatever the temperature amount is, we can add that on to the temperatures for the weather station, hold relative humidity constant, put those values into the wet bulb function, and then feed them into the wet bulb globe temperature function, and then go again with our labour capacity evaluation to see how that propagates through to this impact metric. So just to simplify, what we're doing here is just going from the metrics we already have to which are temperature and measure of humidity, dew point, propagating them through these algorithms to compute humid heat metrics, including at the end this impact relevant metric, which is the labour capacity. And what we're doing here is perturbing those input variables according to plausible scenarios. So increasing temperature, relative humidity stays fixed. We can of course use a climate model to guide that temperature increase, ideally also to guide the change to humidity, but if it's not available for us for whatever reason, this is a simpler way of doing things. Then seeing how it drives or how it affects the impact. Because the impact is going to be highly non-linear, isn't it? It's about threshold crossings. It's very difficult to work this out beforehand, to guess what the answer is going to be. We have to propagate the inputs through these algorithms to see what the impact is. It's highly non-linear. And for Doha, well, it was an area that's very hugely heat stressed, becomes more heat stressed as the climate changes. For Belgrade, you'd have seen probably about like a doubling of the amount of time that you have to rest for 1 degree local warming scenario. So it is a toy example. If you want to do this in a sort of in anger for research, the right question would really be not how much activity is reduced in the peak hour, but how much total time is lost. What's the overall average loss per climate warming scenario? That would be an interesting question to ask, I think. So then the going further bit, hopefully some of you got to this point in producing other temperature scenarios for other climate change projections. All you had to do for this point, if you're not used to Python, it's still quite a lot to take and to read. But you would change anywhere you see 1 degree, you change it to 2, we change it to 3, whatever the value is you're interested in. So otherwise we would overwrite the variables that are in the recent data frame. So we could change this to 2 degrees if we're interested in a 2 degree scenario. At this point, it's just a label in a data frame. It doesn't actually, the 2 degrees we write here doesn't do anything different to the data. It's just a label that we're using. The change in the projection comes here at this point. It's the only bit we need to change. So in terms of actually generate a different projection, we just change that to whatever number we're interested in. If we're interested in 2 degree of warming, we'd have 2 there, 3 degrees, 3 there. The other changes are just to make sure everything's labeled correctly. In the data frame, we don't overwrite things. So for this toy example, if you change that to 2, if you're interested in 2 degrees of warming, we just change these to also to 2. When we see a 1, change to a 2. It would produce a new column in your recent data frame that would have that warming scenario in there. So for 2 degrees, change all those to 2s, change the 1 to a 2 there, run the code, it will produce a new scenario. And then you could have many lines, or 3 lines on this plot if you added a 2 degrees. You could have 4 lines if you added a 3 degrees as well, etc. So that's a nice toy example, just seeing how you can do this. And I said you may want to try other locations. So hopefully, if you didn't get to that point, you can also play around with this and try and find some really hot places. I don't think you'll find many places hotter than around the Persian Gulf, but welcome to try, have a hunt. Then hopefully, if you didn't do any of that, the last bit is hopefully where I hope I leave you with something really useful going forward if you're interested in this type of analysis. This is an illustration of how we can use this code to do analysis to all the weather stations that are in the archive. So now we're going to loop over all the weather station indices rather. The indices of that stations, so so I know we've spoken a lot, gone back and forth. The stations variable is that CSV file with all the metadata in. The index for that data frame we read in are the IDs for all the weather stations in the archive for all 9,200 something weather stations. So if we have any analysis that we do to one weather station, if we put that in a loop, and a loop in programming is just something that's repeated as many times as we want it to, so it's repeated as many times we set the loop up to iterate. What we could do is put all that code for the station analysis inside a loop and just change the station that we're reading in each time. And we'll do the same analysis for every weather station, different weather stations. So in Python, this is the code we can use to loop over the stations. The variable called ID will take on different indices within the station's variable. So that means different station numbers, different identifiers in the HAD ISD archive. And if you remember, we were using the ID to build the URL to download the file in the first place. So you see here, this is the key bit for getting a different file every time. Within our loop, and in Python, you define the loop contents by indenting. Within the loop, we define, and sorry, just one more thing. I've added another layer of indentation here, just to keep it manageable. I'm only processing stations that are in the subtropics. Otherwise, we'd have 9,000 stations processed here. So this is just an if function that checks the latitude and checks that we're between 2 bounds and then does the analysis if we are. But then here we define the unique URL, and then everything is the same after that as it was before. You just copied and pasted the bits of code into the loop. The weather station is changing every time. Now that's the difference. So we can run this for every station worldwide or for a select group of stations worldwide. And whatever we put in this block of code, whatever's indented, will be done to each station in turn. So you can take this straight off the bat, and whatever you put in this block will be done to all the weather stations. So you use this in your future analysis. And it's interesting to look at the output just very quickly to return to physical quantities again and think about impacts. We're just printing out the maximum wet bulb temperature, maximum wet bulb flow temperature. And you can see that we have some extraordinarily high values of wet bulb temperature in the record, including one value apparently at 38 degrees Celsius, which is well above that threshold for human tolerance. But having worked with this data set a lot, you'll see in the Raymond et al. Paper, we employed another layer of quality control over all of this, and that would have been thrown out at 38.1. So the final word of caution, this is a quality control product. But when you really dive into the details and write lots more code to inspect every value in there, when you're really interested in the most extreme conditions worldwide, then you can find some little bugs in there. So hopefully this bit at the end will be useful. If you're not used to Python, there will just be a lot of new stuff. If you are, then hopefully you followed all of those the application to a new environment, a new task, that being automated retrieval of data from one station archive, computation of human heat metrics, etc. And hopefully you can now see how things that are familiar to you can be applied in this context. If you're new to it, hopefully you've now seen the power of programming, how easy it can be to do this type of analysis, to process all the weather stations in the world in this archive. And that's the template at the end, is there for you to use as you see fit.